So other questions? Life is good.
You get all that.
Oh, no, I'm pretty sure it's just notepad.
Just notepad being notepad.
Yeah.
So let's talk about trees in Java. Just trees in general. You're working with decision trees in PA4, but we haven't actually talked about coding up any kind of tree by hand in Java. And I want to run through some code to do that today because it may help you with your decision tree. You may have already done it on your own. But there's a detail that can make it a little different from what we do in C. So let's think about a tree class. And what do we need to have inside our tree class?
Left and right.
Maybe.
Yes and no for this one.
Or yes and no, right. Left and right refer to the children of a node, right? So we need a node, we need at least one node.
Do
Maybe.
you want to make like a class that encapsulates the nodes? Like
So I would
list?
strongly suggest
Making a tree.
A separate.
Yeah,
making a tree node class and making a tree class.
Okay.
Just like the word list.
Kind of like with the word list, yeah. And so a tree node is definitely going to need a left and a right. And what else does it need?
Data.
Needs data. So let's just stick with ints. And it may want some other stuff.
Like color.
You may want to color. But in your decision tree, it might be left, it might be yes, no, right? Or you can just remember yes is left or whatever. So if we have T nodes like this, then what do we need in our tree class itself?
I think you need a root node.
You want some kind of handle to the tree, right? So a T node root. And we may as well set it to null up here, although we could do that in a constructor. And in our main program, what kinds of things would we like to do with a tree?
Traverse.
Traverse,
Add nodes.
add nodes,
Remove nodes.
remove nodes. What's the first thing? What are we going to do before we add nodes or traverse?
Oh, you want to
Create
create
it.
a tree?
Create it, yeah, we need to construct it. So we might do something like this, tree T equals new tree. And probably nothing we have to pass to the constructor. We could pretend to do something fancy, like take the number of nodes you expect to have and not do anything with it. But we want to construct a tree somehow, right? And then we might do something like t.add 15, t.add 12, t.add 14, right? And then we might do something like t dot left node right to do an in-order traversal. And we could do deletes and all kinds of other things, but this would be a pretty good test of whether we've got a basic functionality of a tree working, right? So our tree class is going to want an add method, and it's going to want a traverse method, and so on. So what might our add method look like? Void add integer and maybe void left node right does some sort of traversal, and there could be other stuff in there as well. So here's where the one kind of, not quite a complication, but the one difference comes from what we did in C. Remember in C, when we're trying to add a node to a tree, there were two sort of basic approaches we had. In fact, most of our algorithms fell into two sort of categories of algorithms. Do you remember what those were?
Dynamic?
Close.
Was it recursive?
Recursive.
Not recursive.
and not recursive, iterative, I call it sometimes, right? So when you want to insert into a tree, you can begin at the root, decide whether to move left or right, make that move, look at that new root, move left or right, keep going until you get to a leaf, and then tack your node onto the end of that. And you can do that inside a loop without any recursion at all. But we can also do it recursively, where we say, if the tree is empty, let's just return a tree containing one node which has our data in it. That's the base case. Otherwise, if our data is smaller than the root, insert it into the left subtree. Otherwise, insert it into the right subtree. Right? And then we almost had to do no work at all, except for inserting into an empty tree. But when we took the recursive approach, we needed our insert function, our add function, to return a tree so that we could say something like root.left equals, or root arrow left equals insert parentheses root arrow left comma data. Right? So for recursion, we needed to sort of be able to give you back a tree that's been modified by having this node inserted. So let's think about our add routine here. Our add routine is a method inside the tree class. And we might try to write something like, if n is bigger than root.data, assume root's not null, if n is bigger than root.data, then we want to insert into the right child of root, which we would do recursively by saying root.right.add. But root.right is not a tree. Right? Root.right is a tree node. So if we're going to do this, we have to do one of two things. We either need to get rid of t nodes, make this a thing that actually has a left and right, and put our methods in here, or we have to have an add method inside our tree node class. And I'm going to suggest that that's probably the cleaner solution, is to put an add method in here. Think of add as taking a node and saying, treat this as the root of a tree, and add this node to that tree. And so if we do that, our code's not too bad. We don't have to deal with the null case, because this is going to be invoked as an instance method, which means we have an instance of a node, which means we're not in the case of an empty tree. So we'll deal with the empty case over here in the tree classes add. So all we have to do is say something like, if n is less than data, and then we can say left dot add n. But we do have to deal with the case where left is null. Because if there's no left child on this particular node, this will throw an exception. So if n is less than data, we have to do two things. See if there's a left child. If there is, just use that child's add method. If there's not, create a new node, set left equal to that, and we're done. And then we can do identical things if n is not less than data. And then over here, our add method is simply if root is null, set equal to a new t node. Otherwise, just add this using the root's add method. And left node right is the same. If the left child is not null, do left.lnr, and then print out the data, and then if the right is not null, do right.lnr. And here we just check the root. If the root's null, we don't do anything. Otherwise, we call root.lnr. And we're done. Does that make sense? So let's put this into some code. We're going old school here. So what do we need? We need a left child. And then we want an add method. So add to a tree rooted at this node. We'll go ahead and make it public. And let's make a constructor, because over here we're going to have to see if the left child is null, and if it is, we're going to have to create a new node and make left equal to that. We're going to have to do the same thing on the right child, and we might have to do that up here also. So let's make a constructor that actually builds a node for us with a piece of data, just to simplify our lives a little. So this will build a tree containing a single node. So we'll set the data field, and we got to use this here because if we just say data equals data, we're not doing anything. But I don't need to say this dot left because there's no ambiguity. What I mean by left or right, it's the left or right, that's the T node in the class itself. So there's a constructor. So adding to the tree, so if n is less than the data, add to the left subtree. So if there's nothing on the left to begin with, we go ahead, we construct a new T node with a data value of n, and we just make the left child of this tree equal to that. And now we've got a single node on the left, which is what we want. Return. So if left is null, then there's no left child. Otherwise, otherwise, just use the left subtree's add method, or the left child's add method. So that takes care of inserting into the left. We can assume for convenience that we're not worried about the case where you're inserting something that's already in the tree, and this code will insert on the right if that is the case, because we're not going to bother checking. We're just going to assume we're inserting on the right in this case. So if right equals null, we'll just go ahead and make a new T node, set the right equal to that, and return. Otherwise, use the rights add method. So there's our add routine. Does that look reasonable? So traversal code what the heck was that?
Sounds like you're doing
I'm back to C.
Yeah, I know. Right, so that's about the most beautiful version of a recursive function that we could do at this point, right? LNR, if left is not null, left.lnr, print out the data. If right's not null, right.lnr. And I'm going to print my data side by side, so I won't put a new line at the end.
Oh, I see.
And so that's probably sufficient for our T node class. So all right, so our tree class, we need basically a root, which is a T node. We initialize it to null. So our add method has a base case where the root's null. Null, we just create a single node, set the root equal to that. We've got a tree now with a single node in it. That's what we want, right? Otherwise, there's already some data in the tree. So we have to decide whether we go on to the left or the right. So if n is less than data, then just insert into the left subtree. Oh no, this isn't quite right. Doing too much work. That's easier. So if the root's null, make a single node, set the root equal to that, and we're done. Otherwise, just use the root's add method. And that should give us an augmented tree. All right, so what about the in-order traversal? So if the root's null, there's nothing to do. Otherwise, just call the roots traversal algorithm. And we're done. But I'm going to do one other thing in here before I return. Because our nodes, left node, right, is printing all our data on a single line. When it finishes traversing, our carriage is going to be sitting at the end of some line instead of back at the beginning of column 1. Usually when we're printing, we want to keep things in this reset state. We want our carriage, right, the thing that says where we're going to print the next character, we want that to be in column 1. So the next time we print something, it doesn't come out at the end of our last tree traversal, right? Or in particular, if that's the end of the program, we don't want our bash prompt to come out halfway across the page at the end of our list, right? We usually want a new line at the end. And we don't get that here, but we can get it here pretty easily. Just by doing a print line after we finish the traversal. So that's our tree class. There's a tree. All right, give me some numbers. Give me some more numbers.
12.
4 billion.
We'll do 4 million because I don't want to blow up the integers.
What happens if you do 2?
Do negative 12. Do what?
Just do 2. That might freak you out with also 0, 2.
Yeah, I think we'll just get 2 2s, but we'll find out. All right, one more number. It's got to be the best number of all.
Oh, we already have 42, so that's impossible.
We already do, yeah.
64.
Okay, that's a pretty dang good number. All right, and then we'll traverse it.
So, I was thinking like you don't have your left node, you don't have your traversal thing return a string, but that's not how you have it set up.
Yeah, it's just printing, but we could do a ToString method that returns the in-order traversal. That would be a lot more useful than what we've got. And we can hack up LNR in a minute to see how to do that, because it's a little bit interesting. All right, good. I made a separate directory for this. So I'm going to compile main.java. Hey, not
You
bad.
spelled static wrong, that's all.
Yeah, but you know, once you fix that, then you get like the real story, which is like 80 million errors. Not bad. All right, so I got my class files on my other ones for free because in compiling main, it realized it needed these other, right? I don't quite understand all the rules on how it decides to do that, but let's go ahead and run this and see what it does. Public static void main. Oh, that was interesting.
Oh, you capitalized name.
Oh, yeah.
I did that last time. Why can't they just capitalize every word?
So the kind of informal model is you capitalize class names, right, so that they kind of jump out at you. And so objects, variables, things like that would at least start with a lowercase letter.
Okay.
But then you can typically camel case, make the other words inside a compound name start with an uppercase. All right, so we run that, and that seems to work fine. We got 2 in there twice, which is good.
Nice.
And we got 2 great numbers next to each other. So I go through this, like I say, because it's a little different. If you try to sort of do your add method just in the tree class, it kind of munges things up, right? Unless you also put your left and right child inside the tree class. And then every node has a root inside, which is kind of meaningless, in addition to having a left subchild and a right subchild and a piece of data. And that's not horrible, but it seems logically, to me at least, it's cleaner to sort of have nodes and then trees that are comprised of nodes, and do the recursion in here. So what if we wanted to do a ToString? So let me be a little careful here. We're in the node class here, right? When we work inside main, we're going to want to do something like this. Right, just concatenate your tree to a piece of text. And if we do that right now, it'll just give us that @ sign, class name @ sign, and a funny hex number. So T is a tree, right? So we need a ToString method in our tree class. So we'll initialize a string. And then how are we going to do this? How are we going to call something in our node class that's going to return a string to us? If we want to stick to doing this recursively, if we just iterate, we can just write some code here in a loop and just keep tacking on to S.
Couldn't you put a ToString into the nodes also?
So we can put a ToString into the node class, so what should that return?
Whether it's a leaf or not.
Whether it's a leaf or not.
But we'll probably want to make that into the Q array.
So
Yeah.
I'm thinking you could do exactly what you're doing with left and right, but return strings every time.
Okay.
I'm thinking you could say return the tree on my left, then add myself onto that, return tree on the right, and then return that.
Okay, that's good. That's nice and recursive. How do we return the string for the tree on the left?
You could just say, like, you could have a null case, right? If there's
Mhm.
null, don't do anything with it. Or if null, make it nothing.
Okay.
And you could just say return left dot ToString plus self data, however you want
Basically
to do it.
concatenate it to the string that you
And then
currently
plus
have.
right dot ToString.
Okay.
Or however you start it. Yeah. Yeah, you did that to me. No.
We're in the tree class still.
Oh, okay.
Right, so we're just going to call the roots
Yeah.
ToString method, right? Unless root's null, in which case we'll just return.
Couldn't you just return root?
I don't know if it'll cast it to a string for me in a return statement.
Okay.
I guess,
But we
yeah,
could
if it's-
concatenate it to a plus or something. That would be cool.
If it's null at this point, will it yell at you trying to call ToString?
Yeah, I'll
Okay.
get a null pointer exception.
Okay. Oh, you can't really do that, can you? Because I was thinking, because that's what you could do in C. You could say if this is, no, you can't. Never mind.
Yeah.
Okay. We were on the right path.
Yeah, so left is a T node. We can check to see if it's null. If it's not null, we could say s equals s plus left dot ToString, but when we concatenate to a string, it should turn it into a string automatically.
Default functions for like to int or something? Like if you're casting to an int, will it try to call a to int string or something?
I don't think so.
Okay.
I mean, it knows something inside its brain about doing conversions between, say, a float and a double or an int and a double.
Strings are a pretty unique case.
But strings are kind of a unique case, yeah.
So that's totally reasonable.
yeah, they're pretty unique.
Exception.
All right, so let's concatenate the data and throw a space at the end of it. And then we'll concatenate the right if the right's not null. And then we'll return S. Look good?
Should work perfectly.
Find out in a second.
Hey,
Look at that.
good job. Strings in Java are nice, yeah. So I mean, this is like the hardest part of this is sort of visualizing what you would like it to do ideally, and then it's a few lines of code that sort of say exactly what it is you're visualizing, right? Have a string, tack on the left version, you know, the string version of the left tree plus the data plus the right. All right, so that's fun stuff. I'm going to post this code. I don't have a network connection though. I'll post it later. All right, so questions, other comments? All right, cool.
So for P4, we're doing kind of the same setup, but we are getting the input from the file.
Right, so for PA4, you're still making a binary tree. We're thinking of left and right as yes and no, but it's still a binary tree. Each node has two children. In the very beginning, right, you read database and you build your tree. And that's that recursive algorithm that I called ingest, right? So read the first two lines in your file. If it's an answer, just make a tree containing a single node and return that. If it's a question, call ingest again, whatever tree that returns, make that the left child of your tree. Call ingest again, make that the right child of your tree. Make the root of your tree whatever that question was that you read in the first place, and then return that possibly bigger tree as your function value. So it's a recursive setup. And then to play the game, thank you. To play the game, you probably don't want this to be recursive. Okay, this is probably easiest just in a straight loop. Just start at the root. If it's an answer, the game is over. Tell the person what the answer was and carry on from there. If it's a question, ask the question, get a yes/no response, and then move your attention down to either the left subtree or the right subtree. Go back to the top of your loop and do it exactly again. Right? If it's an answer, print out the answer and you're done. If it's a question, print the question, get a yes/no, move to the left or the right, and keep going. And I think that will get really, really weird if you try to do it recursively. it would be a tail recursion, so you can always unroll it. It'll be something where you're just recursing once at the very bottom of your loop, so you don't really gain a whole lot.
So the first time it keeps asking the user questions, because that's how it builds it. And then finally when you're trying to you get it.
Say it again, what do you mean the first time?
So it has to ask the if it's a no, it has to ask the user, okay, what would be the question?
You mean if they got if you're done playing and the answer was wrong? Right, okay, so you get down to your leaf node, it's an answer, you say, okay, you're thinking of a rock, and the user says, no, I'm not. Okay, so rock, and it's no, so this was answer rock. Okay, so actual answer was a turkey. Okay, so how can I tell the difference? So give me a question for which a rock would have a yes answer and a turkey would have a no answer. Okay, can you eat it?
Maybe
Should you eat it? Maybe we should eat rocks, I don't know, maybe they're healthy. So we change that to, can you eat it? It's a question. The yes answer would be, it's a turkey. And the no answer would be, it's a rock. Right, and you do this in memory, right? So this node, you change its data value to be a question, and you give its left and right children, instead of being null, make them new nodes, where that's a turkey, that's a rock, right? And now you got a smarter tree, right? It's going to do better the next time, and
It's a learning movement.
it's learning. And if you were wrong at the end, update the tree and write to your file. And then go back and play the game again. So we only read from the file once in the very beginning. And after that, the only thing we do with the file is we just overwrite it. Right? If we change the tree, just rewrite the whole file. And the way we rewrite it is by doing a pre-order traversal. So left node right, and instead of printing it out to the screen, you print out your data into this file. And what's the class I suggested using for that? Print writer. All right, anything else?
We don't have to be prepared for an empty file, or do we?
No, I will give you a file that contains at least 3 nodes, a question and 2 answers. You can do it, it's just, it's more edge cases, and I'm not so interested in edge cases at this point. I'm more interested in watching you make a decision tree and do some recursion and stuff like that. Let's talk about RegEx for a little bit. So we all love regular expressions. They make your life easy. They stop Window Builder from crashing shamelessly when you get to Java version 10. And there's some nice packages available in Java for working with regular expressions. And the main class is pattern. So you can read the Java documentation on this, and it's got, you know, a gazillion methods and stuff. But let me show you a basic way to use this. So we can do something like pattern. Let's try to parse an assignment statement. So we want something like, you know, x, y, z equals 12, or I equals 17. So we want to parse a set of characters in a string and see if it matches a pattern like this. Okay, so regular expression rehash. Suppose we want the thing on the left to be one or more uppercase letters, and then we want an equal sign, and then we want one or more digits. And that's the only thing we're going to consider to be valid. So how do we specify in a regular expression we want to match something from the beginning of the line? Caret. Okay, so caret says whatever comes after this has to be in the very beginning of the line. How can we ask it to match an uppercase letter?
Like, do brackets and then list all the uppercase letters.
Well, it is.
Yeah, it's nice enough to let you do this. Okay, how do we match one or more of these things? Asterisk.
It's like catch-all.
Right. With one small detail. So an asterisk actually says 0 or more occurrences.
Oh.
So if we want to match one or more, we could do this. So now it's got to be a letter followed by one or more, 0 or more letters.
You can also do a plus if it supports extended regular.
That's true. I don't know if it does. It probably does. This would also let you say that the first character has to be a letter, but the following characters could be letters or numbers. So we could do A through Z, 0 through 9, things like that.
If you wanted to say 0 or more anything, right?
Mm-hmm.
0 or more characters.
Mm-hmm.
How do you do that?
Dot star.
Dot
Dot
star.
matches anything.
Okay.
And dot dot star would match anything that has at least one character in it. All right, so let's make some space. So that's going to match the left part of our assignment statement. How do we match an equal sign?
Equal sign.
Equal sign, all right. And how about one or more digits?
Basically the same thing. you did
Basically
with
the
letters,
same
but with
thing.
the numbers instead.
So when you do that through, is that like the ASCII code?
Yeah.
Of this character, this character?
I think it's ASCII. It's effectively ASCII. It might be doing something more modern, like Unicode ordering
Yeah,
or something. I don't know.
Unicode works the same way.
Yeah,
They're all next to each other.
yeah, as they should be. All right. Anything else we need on here? $sign to say that after those digits are done, that should be the end of the line. Otherwise, I equals 17, haha, would parse, and it probably shouldn't. So if we say pattern assign equals, and there's a static method called compile in the pattern class. So if we call this compile method and we pass it a string, which is a regular expression, it will create some kind of internal representation of this, and in this case, this is in a pattern object that we called assign. So pattern assign equals pattern.compile parentheses quote, regular expression gives this assign object what it needs to match something against this regular expression.
So is compile a void, or is it, was it return?
It returns a void, yeah. Or it is a void. Well, no, it returns a pattern.
Yeah.
Yeah. Sorry, I broke this out on 4 lines because I didn't have space. So this is returning a pattern, right? So once we have that, we can do the following. Assign is a pattern now. It has various methods, including something called match. So you have an input string you want to compare against this regular expression. Let's just suppose it's called input. So that's a string. You can say assign dot matcher, give it that string, and that will return an object of type matcher. And then that object has a matches method. And it'll return a Boolean saying whether or not you actually match this input match this pattern. So it's sort of a multi-step process, right? First you compile a pattern. You use that compiled pattern, use its matcher method on an input string, that returns a matcher object. And that matcher object has a method that tells you whether or not your string matched the pattern that was compiled. But we can also group pieces of this using those parentheses around pieces, and things that match stuff within a parentheses will get thrown into a register, and we can pull off the registers using this matcher object also. So we can say m.group1, m.group2, and so on, and that takes the place of those backslashes that we used to work with, \1, \2 to read the value of a register. So we could not only tell whether or not an input string matches this pattern, but we could throw parentheses around here. And now m.group1 would be the string representing our variable, m.group2 would be the string representing our integer. And then we could throw this into a hash if we wanted, and we could parse the integer and store it as an integer, and now we're building a symbol table where we have a list of all of our variables in our hash map, and with each variable we have its current value associated. So now you're starting to build a compiler. And these kinds of tools make that pretty fun. All right, we're over time. So tomorrow's Friday. All right, so no class on Monday. So Tuesday we'll probably talk about Huffman coding, or maybe more about regular expressions or questions if you've got them.
You can finish it, I guess.
Well, technically, we just went through the. Yeah, there's that.
Well, we ever need to like put together